300 kilometers per hour is a speed often reached by luxury supercars flying down German roads. However, the nation holds even greater pride in the highway system itself, where the concept of a speed limit almost does not exist. Why does such a high-speed network remain one of the safest on the planet? At first glance, driving without restrictions seems dangerous. But in reality, American engineers study the Autobahn because it operates on a distinct philosophy. It seems simple to pave a road, but this is just the beginning. Builders do not simply pave over the soil, as acts as the norm elsewhere. A roadway here must be built like a complex engineered structure from the ground up. One can notice how the construction layers are stacked with precision rather than just covering the earth. The camera glides along the asphalt, revealing a surface designed to withstand extreme forces. Special standards in cutting-edge construction technology define every kilometer. This transforms the Autobahn into the gold standard of modern transportation engineering. It does not end at this stage. The analysis of these hidden standards begins immediately. 357,000 square kilometers is the total area of Germany, covering less than half the size of the American state of Texas. Yet, the country maintains a highway density 7 times higher than the United States, with more than 8,000 miles of Autobahn stretching across the landscape. One can notice how the infrastructure connects every corner of the nation. But this is just the beginning of the engineering distinction. Unlike many countries that simply lay a layer of asphalt, Germany follows a philosophy where a road must be thoroughly built. Why is the structure strictly formed around 4 key layers? At first glance, a single thick coating seems sufficient for traffic. But in reality, the system starts with a compacted subgrade foundation and a stabilized subbase. The equipment gradually installs a load-bearing base course before applying the high-performance asphalt surface. This multi-layer complex prevents cracks, deformation, or rutting, even when vehicles travel at speeds of 300 kilometers per hour. It gets more complex further on. Engineers utilize advanced polymer-modified asphalts capable of withstanding summer temperatures of up to 70 degrees. It is visible how the material remains stable in heat, yet stays flexible in winter to resist freeze-thaw cracking. Thus, high speed is safely supported by these rigorous construction technologies. 25 to 35 tons of impact force are required to prepare the ground for world-class construction technology. But the process begins in the quiet of the forest. Why do technical teams spend months on geological surveys and terrain analysis before a single tree is felled? It would seem faster to simply clear the path and build immediately. But without this long preparation phase, the road foundation would lack the necessary data for stability. These detailed steps determine exactly where the road will run, how thick each structural layer needs to be, and which soil stabilization methods are suitable for each section. Only after all the data is fully reviewed and approved are crews allowed to begin actual on-site construction. Clearing all trees, vegetation, and topsoil is the priority job when the construction site is officially handed over. One can notice how excavators strip away the landscape to expose the original ground underneath, removing every trace of organic material. This step is essential because any remaining roots or soil can cause settlement or instability in the road foundation later on. But this is just the beginning. Crews begin cutting and filling the terrain to shape the route once the area is cleared. High hills are lowered, and low areas are carefully filled in to match the designed elevation, ensuring a continuous, smooth roadway without breaks or uneven levels. To make the ground level and stable, heavy vibratory rollers enter the scene to compact the soil. Depending on the specific soil type and moisture level, the operators usually make 6 to 12 passes. It seems like a simple, repetitive motion, but in reality, each vibration delivers an impact force of about 25 to 35 tons. The goal is to bring the soil up to the standard Proctor density, strong enough to carry the huge loads of European trucks. Next, heavy trucks bring in crushed stone and unload it section by section along the road. A grading machine spreads the stone evenly, covering the entire surface to match the designed elevation. Transition to the next level. One can see a water truck spraying a thin layer of moisture to help the stones bond better during compaction. A bulldozer then reshapes the layer, making sure the thickness and flatness meet the required standards. Finally, a large vibratory roller compacts the material through multiple passes to create a strong upper base. This crushed stone layer acts as the load-bearing foundation, helping distribute vehicle pressure into the soil below and increasing the durability of the entire pavement structure. The concrete base layer is ready to be poured, now that the crushed soil and rock surface has been leveled and compacted. 40 centimeters of solid concrete structure begin to take shape as heavy trucks arrive at the site. Why is the ground pre-covered with bright white protective sheets before pouring? To the eye, it looks like simple cleanliness control. But this barrier prevents ground moisture absorption, ensuring the mix retains its precise water ratio for maximum strength. Trucks carrying pre-mixed cement with the correct consistency enter the section, lifting their drums to unload fresh material. An excavator immediately scoops each batch with a large bucket to transfer it into the hopper of the slip-form paver. Continuous loading guarantees the machine receives a steady supply without interrupting the construction process. Inside the paver, an internal auger system spreads the material evenly across the full width of the road. It seems the mix is already dense, but in reality, high-frequency vibrators remove hidden air bubbles to ensure uniformity. A shaping mold at the rear then presses the concrete to exact design dimensions from thickness to cross-section. But this is just the beginning. The entire operation relies on a laser-controlled system that guarantees precise smoothness and slope. The machine constructs dozens of meters of roadway in just a few hours. Steel dowel bars are placed into the loading tray above the machine to be inserted into the fresh concrete. These bars increase durability, prevent cracking, and transfer loads between adjacent slabs. It gets more complex further on. The mechanical system automatically pushes each dowel bar into the concrete at the correct depth and spacing. This positioning ensures the slabs remain stable under traffic, allowing the roadway to behave as a continuous structure. Right after shaping, long finishing arms sweep across the surface to smooth the top layer. One can notice how the blades eliminate waves to achieve the required high-speed roadway finish. This step is crucial for ride comfort. And this is not the limit. The concrete layer is usually 40 centimeters thick when a spraying truck applies a curing compound. This protective layer, usually paraffin-based or acrylic, forms a thin film that slows water evaporation during hardening. This process helps the material reach its optimal strength without defects. After 30 to 60 minutes, specialized brushing machines arrive to texture the pavement. It is visible how high-speed rotating brushes create fine grooves on the top layer that improve tire grip. This step also removes excess cement dust, leaving a clean and uniform surface. Finally, a specialized cutter creates expansion joints at design intervals to control cracking and protect the pavement structure. The concrete will be left to cure for several days. Thus, the foundation is fully prepared for the subsequent step of asphalt paving. (160°C) is the critical temperature maintained for the hot asphalt mixture inside the dump trucks. The heavy vehicles unload the scorching mass directly into the receiving hopper of the paver to begin the most important step in building a highway. From there, the internal conveyor system and rotating augers continuously move the material toward the rear mechanism. One can notice how the black mix spreads evenly across the full width of the future road. But this is just the beginning. The real technological magic happens at the screed. a complex unit located at the very back of the machine. Why does the equipment rely on vibrating, tamping, and pressing units simultaneously? At first glance, simply spreading the asphalt seems sufficient. But in reality, this combination allows the paver to achieve 85 to 92% compaction while the material remains extremely hot. This creates a shaped, compressed, and smoothed layer in a single continuous pass. This method proves especially effective for surface coarse or stone mastic asphalt, which is applied in layers only 2 to 3 centimeters thick. Such a thin coating cools very quickly, making traditional methods risky. Using heavy vibratory rollers on this rapidly cooling mat can often cause surface cracks or unwanted ripples. However, with the automatic screed found on modern European and German pavers, the road surface remains perfectly smooth and well textured along the entire stretch. It gets more complex further on. In the past, achieving proper density required a fleet of multiple rollers, including vibratory, static, and pneumatic machines. Today, high-end asphalt pavers handle more than half of the compaction work inside the machine itself. The Vogel pavers from the Vergen Group are especially well regarded for their precision and material efficiency. These machines reduce the need for subsequent roller work by 70 to 80% compared to older methods. One can see the machine moving steadily, leaving a finished, high-density product in its wake. And this is not the limit. After paving, a light steel roller may make one final pass to finish the surface, though many modern projects skip this entirely. The mat often already meets strict standards straight out of the machine. Thanks to this advanced technology, the process becomes faster and more consistent, ensuring long-lasting highway quality for years of operation. 180 to 200 degrees Celsius is the critical temperature range. The thermoplastic paint must reach inside the specialized striping machine. Once the asphalt has cooled and reached full stability, the crew employs laser measuring tools or guide strings to determine the exact position of every lane divider, stop line, and directional marking. Why is such intense heat required for simple road lines? The mixture appears liquid and volatile in the tank. The high temperature is actually necessary to ensure maximum adhesion to the porous asphalt surface, fusing the materials together. As the machine moves, its spray head creates lines with the precise thickness and width required for strict highway standards. But this is just the beginning of the safety measures. One can notice how a curtain of tiny glass beads is dropped onto the fresh paint immediately after spraying. At first glance, this seems like a decorative finish, but in reality, these beads are essential for reflecting car headlights at night to significantly improve visibility. After just a few minutes of cooling, the markings harden and bond firmly to the pavement, completing the road surface. Because the surface is now complete, the focus shifts to physical containment. The final step involves installing concrete barriers, which are usually precast in a remote factory before being brought to the construction site. At the factory, workers pour concrete into high-precision steel molds to ensure all dimensions and angles are perfectly consistent. It is visible how vibrating tables shake the molds to compact the concrete, eliminating air bubbles and creating a smooth surface. This process increases the structural strength of the barrier significantly. And this is not the limit of the preparation. Once the concrete reaches full hardness, each barrier is removed from the mold, rigorously quality checked, and numbered in the order they will be installed. Therefore, when the units arrive at the site, cranes or specialized forklifts can place the concrete segments exactly where the plans specify. Workers then secure them together using steel pins or bonding adhesive, forming a continuous and stable barrier line. This precast installation method speeds up construction and reduces road closure time efficiently. The engineering team immediately conducts a final inspection of the entire highway structure. They rigorously check road smoothness, drainage performance, surface traction, and the structural quality of every section. The camera glides along the finished surface as engineers verify that each component fully meets all safety and technical standards. Everything must be perfect before the handoff. Only then is the highway allowed to open for use, marking the end of the project. 8 to 15 years is the typical operational lifespan of a highway surface before it requires critical intervention. Heavy truckloads, weather impact, and the relentless cycle of freezing and thawing gradually wear down the asphalt. Before any road is initially allowed to open for use, it meets all safety and technical standards, but time eventually erodes this integrity. The surface loses its smoothness and grip, signaling the need for recycling to restore its structural life. But this is just the beginning. The restoration process starts with the arrival of heavy milling machinery. Why do engineers remove only a specific layer depth of 2 to 10 centimeters? At first glance, milling seems like a superficial solution for a damaged road, but in reality, the underlying basin structure usually remains intact, and removing only the worn top layer is sufficient. This approach significantly shortens construction time and reduces costs compared to rebuilding from scratch. One can notice how the milling machine grinds the old asphalt into small pieces and collects them onto a conveyor belt. The belt moves steadily, loading the material directly into a truck following closely behind. This material, now known as reclaimed asphalt pavement, is transported to a recycling plant. There, a complex screening system sorts the fragments by particle size. The equipment gradually removes impurities such as soil, oversized stones, or accidental metal pieces. Because the reclaimed asphalt has aged differently over years of service, proper sorting is vital to ensure quality. The usable particles are blended into uniform batches to guarantee consistency in the final product. It gets more complex further on. The sorted material is mixed with new asphalt binder, fresh aggregates, and a special rejuvenator additive. This chemical agent restores the elasticity of the old binder that is oxidized and become brittle over time. At the mixing plant, the material heats gradually to avoid burning the aged asphalt components while combining with the hot binder. Modern plants can utilize 30 to 60% reclaimed material in the final blend. One can notice that the resulting mix performs just as well as brand new asphalt. This efficiency saves natural resources and significantly reduces carbon dioxide emissions. The precise formula ensures the road performs under traffic without failure. Therefore, the road surface must be thoroughly cleaned of dust and debris before the new layer is placed. In this modern process, a single machine performs both the tacking and laying tasks simultaneously. Front nozzles spray a thin layer of asphalt emulsion, known as a tack coat, directly onto the old pavement. This layer acts as a powerful glue to bond the recycled mix tightly to the existing surface, preventing slipping or separation. And this is not the limit. The machine immediately places the recycled asphalt mix onto the coated surface without any waiting time. The paver spreads the hot mix to the strict design thickness while the screed vibrates continuously to establish initial density. One can notice how the surface becomes smooth and uniform in a single pass. Both vibrating and static rollers follow to ensure the mixture reaches the required density, preventing future rutting or cracking. Once compaction is complete and smoothness is verified, the highway performs exactly like new. Zero defects remain on the surface, as the road is now performing just like new. One can notice how the fresh asphalt lays smooth after the heavy machinery departs. This marks the completion of a rigorous engineering cycle. Why encompass the entire process of building, maintaining, and recycling in one strategy? The project scale suggests independent tasks, but in reality, Reliable technical data confirms that integrating these phases ensures the longevity of a modern highway in Germany. Thus, the infrastructure returns to full operation